Yes. Homework 6? Convnets, and transformers. Convnets and transformers. Yeah. I believe it's mostly PyTorch stuff. Yeah. Cool. Surprised to see so many people here today. Yeah, I hope to make it worth your while. All right, we can get started. Transformers, part 2. Okay, what are we doing today? Well, so last lecture, basically all we got through was attention and then talking about self-attention. That was pretty much all I planned to get through last time, but that's what we did. We haven't actually seen what a transformer is yet. We've just sort of laid the foundation for trying to understand transformers. Now that we've done the hard part, it's actually pretty easy from here on out. Transformers are basically just lots of stacked self-attention layers. Remember, we can think of self-attention as a layer that's taking in a whole sequence and then outputting a whole sequence. And we can sort of put these on top of each other in order to, process the sequence into, more and more complex representations, basically. Transformers are sort of like just a bunch of stacked self-attention layers, although we're going to see a slight problem with this, and then we're going to have to amend it a little bit to actually make it what we want it to be. But this is pretty much what we're dealing with here. So we're going to put all these pieces together, and we're going to build different types of transformers, 2 different types specifically, called encoders and decoders. And we're going to talk a little bit about, what role these actual types of transformers play, although we'll do more of that on Friday. When we actually get into some of the applications of transformers, it'll become a little bit more clear then why we build these different types of transformers. Today we're also going to see a whole bunch of the important little details that make transformers work really well. Okay, so there are going to be details along the way where you're probably going to squint at it and you're going to say, what the heck? Like, that looks pretty weird to me. Just know that it looks weird to me too, but a lot of these details are, fairly important, and they do get things to work pretty well. So it's important that we go over them. Okay, but recall, what is self-attention? So we talked about attention, we talked about the motivations there, and then we went into sort of the mathematical detail about how attention works, right? Self-attention basically works the same way procedurally, right? So mathematically it looks very similar, right? Although some of the intuitions that we built for attention don't exactly hold quite as well, the math is still there in pretty much exactly the same way, right? And the goal of self-attention is to be able to handle these types of sequential features as the input. So we get sequences in, and the self-attention layer produces another sequence, right? Sequence in, sequence out. So basically, it becomes this layer that we can put in our neural network that allows for processing the whole sequence all at one time. Okay, that's pretty much the motivation behind self-attention, is really efficient and effective processing of sequences. And remember, it operates according to this key value query system, just like attention does, right, that we detailed last time, where we have, all of these different learned functions, oftentimes just very simple linear functions that we're learning, right? That in the case of self-attention, they all process the same thing, right, which is the input. And then they produce these different queries, keys, and values based on the different parts that I have in my input, usually what I call the tokens that I have in my input. But actually, there's a little thing that we have to amend here, which is the fact that this is what a self-attention layer will be doing if it's the first self-attention layer, right? If it's taking in the actual input and then producing some, representation, right? However, this self-attention layer could come after another one or sometime deeper into our network, right? So in that case, what is its input? It's like some, hidden, representation that's the result of the previous self-attention layer's output, right? So when we start stacking these things on top of each other, what the later layers are getting is not X, the input, it's like some H, some hidden representation that was produced by, whatever self-attention layer came before it. Remember, this is the picture that we drew for attention and also for self-attention, right? We compare the query that I have, for example, at time step 2, so that's why this is Q2, right? The query that I have with all the different keys. And here there's actually, whatever the length of the sequence is, capital T, there's that many number of keys, right? I compare the query to all the different keys using a dot product to sort of measure similarity, use a softmax to get some normalized weights out of this whole thing, and then I produce my output as a sum, a weighted sum of all the different values weighted by those alphas that I've found. Okay, so that's the basic setup for what this attention mechanism looks like. It's basically like trying to, select different pieces of the input or, values extracted from different pieces of the input depending on what it is that I'm looking for at any particular time step. That's kind of the high-level intuition. Right, so if I have an input sequence, I can pass it through a self-attention layer, and I'll get, some output, which is another sequence of the same length, right? But now it's got, now it's like some different representation. Oh, here I called it A. I called it A down here, and then up there I called it H. That's a little confusing. I did that because there's something later on that we're actually going to change about this whole thing. But just for a second, pretend that those are the same thing. For a second, pretend that A and H are the same. Okay, so we can process our sequence into another sequence using self-attention. We can rinse and repeat this process as many times as we like, right, in order to continually process our sequence into representations based on, this self-attention operation that we have. There's a small detail that's important in transformers, which is that this is something called dot product attention or dot product self-attention. The thing that transformers use is actually something called scaled dot product attention or scaled dot product self-attention. It's really simple. Basically, take all of those dot products between the keys and the particular query and divide all of them by the square root of whatever the dimensionality of those things are. Okay, so the keys and the queries have the same dimensionality, right? That's the only way you can dot product them together. When I'm computing these similarity scores E, I also divide by the square root of D just to make it so that I don't get these weirdly large numbers that when I pass through the softmax are going to be like really spiky and stuff like that. That's basically the only reason. And they found that this tends to work better than not doing this. Right, so we got self-attention. All right, this is self-attention. Let's take this idea of this layer that we now have for processing whole sequences and try to use it to build the transformer. Attempt number 1. Can we just stack self-attention layers on top of each other in this way that we've sort of described? So we have this whole sequence X. It gets processed into some other representation A1, which is another sequence using self-attention. We do that again to get, A2, so on and so forth. There's a slight issue here. Can anyone figure out what the issue might be with this type of approach? Think back to the issues that we had with all of our previous quote-unquote attempt number 1s. Yes? Yeah, so we're sort of in the same boat as what we had before with like the attempt number 1 for convnets, the attempt number 1 for fully connected networks, et cetera, et cetera. It's a little bit more subtle this time, okay? So we have to write this kind of carefully. Basically, the problem is that each output is a linear combination of the values. Okay? We took a weighted sum of the values where the weights are given by those alphas, right? So with respect to the values, the V's, the output is linear, okay? Not with respect to like the K's and the Q's, right? Because we pass those through a softmax, that's nonlinear, but the values, with respect to those, it is linear. Oftentimes, values are produced by a linear function on X, on the input, Okay, that's like the v function, right? And usually that's just something like a learned linear function. So the values are a linear function of the input, and then the output is a linear combination of those values. Then what essentially you're getting is that the the output, right, is a linear combination of your input. Right? Those weights are something nonlinear and kind of complex, but at the end of the day, you're not really getting anything more than just some linear combination of the x's that you have. Okay? So every single like A1 here, right, like every dimension, like A11, A12, so on and so forth, all of those are linear combinations of x1 through xt. Okay? The weights for the linear combination are complex, but at the end of the day, it's still just some linear combination. You stack those on top of each other, you're still just getting linear combinations of the original thing that you started with. Okay? So it's not quite as simple as what we were saying before with like the fully connected networks, the convnets, but the general principle underlying it is the same. We're still running into a very similar issue here. So what is a solution that people have found to work? It's basically the same solution that we've used this whole time, which is just add something that makes it look nonlinear, and then just interleave these things. That's the whole idea. So what we're going to do is we're actually going to interleave these self-attention layers, which in some sense are kind of like linear, with what people oftentimes call feed-forward layers. I don't know why people call it this, but this is the term that a lot of people use. These are usually just like simple nonlinear layers, like a linear transformation plus some kind of activation. The most common activation that people use for transformers is this thing called the GALU, which Sean O told you a little bit about. The details are not that important, but this is the most common activation function that people usually use for transformers. So what is this going to look like? Well, basically, I'm going to have my sequence, x1 through xt. I'm going to process that first using a feed-forward layer, okay, which is going to produce me some representation, which I'm going to call H, to distinguish from the A's that are being produced by self-attention. Okay? This feed-forward layer is going to produce, a sequence H1 through H capital T. The feed-forward layers are what we call position-wise. What does that mean? All that basically means is that H11 was produced only as a function of x1. H12 only as a function of x2, so on and so forth. So at every single position in my sequence, I'm running this feed-forward layer separately. Okay, so there's no mixing across time steps that's going on here. That's the self-attention layer's job. This feed-forward layer's job, its only job is to be nonlinear. Okay, but it's nonlinear in a position-wise fashion. Okay, so I pass this through some kind of feed-forward layer. Then I pass it through a self-attention layer, okay, which is going to combine information across all of these different time steps in order to produce what we had before, which we called A, another sequence, right, that can sort of mix together all the different information that I have at all these different tokens along my sequence, which is something that the feed-forward layer can't do by design, but the feed-forward layer can introduce these nonlinearities that turn out to be very important. And I can just sort of rinse and repeat this process as many times as I like. Throw on another feed-forward layer, then throw on another self-attention layer, so on and so forth until I'm happy, that I've built my transformer deep enough as far as I can tell. Pass it through one last feed-forward layer. Maybe the last thing is actually just a linear layer, but we're going to call these things feed-forward to get, maybe what I can consider to be my sort of like my final representations. Everything that I'm doing here is sequence-based, right? So the final representations that I get are still going to be, some sequential thing like Z1 all the way through Z capital T. But hopefully by introducing these nonlinearities and also these self-attention layers, I've processed my sequence to the point where Z1 through Z capital T is a representation that's easier to work with than the original sequence that I had. That's the basic idea. A lot of the times, and we're going to define this in a little bit more detail, a lot of the times, if I produce these like Z1 through Z capital T, people call these different terms based on, the particular application that they're working on. These can be called representations. It's like a representation of the original data that's hopefully a little bit easier to work with. Or embeddings, they might be lower dimensional. or features. You know, we've used all of these terms before. This is what people typically think of when they're using a transformer to process an input, right? The transformer outputs some sequence Z1 through Z capital T at the end, and typically these representations, embeddings, or features, however you want to call them, is what ends up getting used for tasks later on, which we call downstream tasks. And we'll go through some more examples of what downstream tasks actually look like in the next lecture. But for now, the important bit is that these Z1 through ZT, that's kind of like the output of my transformer. That's the thing that's going to be used to do, you know, some other task where you working from this representation is going to be a little bit easier. Okay, so I told you that there's two different types of transformers that we're going to talk about. This is basically the first one. And so we'll do this in a little bit more detail, though. A lot of the times people talk about transformer encoders and transformer decoders, so it's quite good to know what people mean when they say these different things. So let's go over the transformer encoder first, because the transformer encoder is basically just exactly what we just did, okay? A transformer encoder takes in a sequence, right, x1 through x capital T, and then processes it using this interleaved feed-forward self-attention layer kind of strategy into that representation that we were just talking about, Z1 through Z capital T. This is like the encoding of the original input sequence. That's why people call these transformer encoders. And like we said before, we think that these Z1 through Z capital T are somehow going to be useful because they're going to be easier to work with than the original input sequence when trying to solve some new type of task. I haven't really told you anything about how that's actually done. We're going to delay that until probably, you know, Friday. But this is basically what the job of the encoder is at a high level. What does the encoder actually look like? Basically looks exactly like what we were just doing right now. You take your input, pass it through these feed-forward layers, and interleaved with self-attention layers. The feed-forward layers are position-wise. The self-attention layers are the things that mix information across these different time steps. You do this for however many times you like. Maybe pass it through a final feed-forward layer, maybe just another linear layer, something like this, to get your representation Z1 through ZT, which, like we said before, is hopefully going to be something that's useful for these downstream tasks that we want to solve. So in a sense, the Z here, right, it's kind of playing the same role that the Z was playing in like the fully connected network or the ConvNet, right? Like what were we doing with the Z back there? Well, if it was something like classification, we would take that Z and we put like a linear model on top of it, like a logistic regression model, right? We just slap a softmax on top and then do classification, and we're hoping that the Z or the representation that we learn is good in the sense of, you know, being good for a linear model, right? That's what the neural network is trying to do, right? Here you can sort of think of it from the same perspective, the same intuition. This Z that's being output by the transformer, now it's not just a single Z, it's actually a whole sequence of Zs, right? Because sometimes I need sequential information. But this Z is basically going to be fed into some like simple model, and then we're going to hope that that simple model is able to use it effectively to solve whatever task it's trying to solve, more effectively than if it was given the original X instead. That's kind of the high level bit. Well, okay, if this is not yet confusing, don't worry, it gets worse. So there are some important details that we should know about. I think this detail in particular is probably the most confusing one, and it's something called positional encoding. So the basic idea is that actually this second bullet point is important. So the one current problem that I have with the way that this model is set up is that this transformer, as I've described it, actually can't distinguish between different permutations of the same input sequence. Okay. Why is that? Well, it's because I have all these different keys that are being generated from the different tokens in my input, right? These keys have no particular ordering to them, right? I'm just dot producting all of them with my query, right? And then I use those scores to figure out which values should I pick, right? But those are just values almost like in a set, like in a bag, right? Like there's nothing in particular about the positional encoding of these different things that would let me know which order the tokens actually came in my sequence. This is kind of an issue because order matters, okay? We're dealing with sequential inputs, right? The whole point is kind of about the ordering of the sequence that we have, like, you know, what order the words actually came in the sentence or something like this, right? So the order is very important, but actually so far, we actually haven't captured any notion of the ordering of the input. So in order to do this, somebody came up with this idea of positional encodings, which is basically just add something that tells you positional information to each one of these first, hidden representations that I generate. This representation that comes after the first feed forward layer, add a positional encoding there in order to be able to distinguish each of these different time steps. That's the high level idea. The high level idea I think is okay. The low level details look really weird. Okay, so I'm going to show you what this positional encoding looks like, and then we're going to talk about it a little bit, but I implore you, do not stare at this too hard, because the more you stare at it, the weirder it gets. So a very common choice for the positional encoding is as follows. Okay, we have this positional encoding called PT. Okay, let's try to digest this like bit by bit. What is the dimensionality of PT? Well, if you look at this closely, you're going to figure out that the dimensionality of PT is D, whatever D might be. Okay, what is the D that they're referring to here? The D is a dimensionality of this HT that I have up here. Okay, so each HT, right, from 1 to capital T, each HT has dimensionality D. It's like a D-dimensional vector. Okay, each PT, right, which is different for all the different time steps that I have, right, because it's a function of T, as we can see. Each of these is also a D-dimensional vector. What I do with this positional encoding is I literally just add it to the H1Ts. Okay, so it's an element-wise addition to each one of these, representations that I'm generating from the first feed forward layer. Because I'm adding something different to each one of these H's, each one of these HTs, right, I'm going to get different positional information that's then embedded into that resulting vector. Okay, because I'm adding something different to each one of these H's. And the thing that I add in particular is basically just, all these different, sine, cosine functions at varying frequencies, right? Which tell me something about sort of like, at position T, what are the, or like, at this particular position, like how do I infer what time step I'm at? It's based on these different sine, cosine values which sort of oscillate between the different time steps. This thing is the dimensionality of, I already said that. This thing is the dimensionality of HT. Here's a couple of dimensions of what this positional encoding PT actually looks like, okay? So we can basically see that at any particular time step, right, what we're going to get is a different combination of these sine, cosine values that basically tells us some information about what time step it is that we're currently at. And the basic idea is that it also tells you a little bit about sort of like relative positionings. Because we have different frequencies that we're dealing with in terms of these sines and cosines, some of these will oscillate very quickly. And they might tell you information like, am I at an even time step or an odd time step? Because, the thing is oscillating so quickly, right? But some of them might oscillate very slowly, depending on, the particular thing that's actually inside the sine cosine. And they might tell you something like, am I in the first half of my sequence or the second half of my sequence? So you're getting a lot of different types of information here in terms of where you are in your particular sequence. Yes? Yeah, okay, great. So the question is like, does each token have a different dimensionality, D, or are they all the same? They're all the same. So here, I think it's a little bit more, intuitive to think about these H's, which are basically a function of the X's. right? So like each HT is produced by each XT through some simple feed-forward layer, right? All of these different HTs, they all have the same dimensionality. They're all d-dimensional vectors, okay? And then each one of these PTs, they're also all going to have the same dimensionality. They're also all d-dimensional vectors. And that's why we can just add these things to each other. Yes? Great question. So I don't have this slide. The question is basically, how would this compare if I just like appended T to each one of the H's? People have tried that and found that it kind of works worse, maybe because like it's not like the most generalizable representation. Like one problem, right, is that it's difficult to generalize to longer sequences than what you have in your training data, because you start to append things like, you know, capital T plus 1, capital T plus 2. Your model's never seen that before. It can do some kind of unpredictable things. I think that a lot of, you know, these design decisions, like not to say that like this is the best thing that we could come up with, but it seems to capture some notion of like, you know, what's easiest for the model to digest in terms of like, you know, the different types of representations of time information that we could give it, if that kind of makes sense. Yeah. Why do you add it after the first layer? You mean as opposed to like the input or something like that? Or after each layer? Okay, yeah, so this is a good question. So my understanding of why you don't add it to the input is that the input is actually, for example, for something like text, it's like one hot vectors, which kind of makes it a slightly stranger choice based on, you know, some of the actual like implementation details of like how this first feed-forward layer actually gets implemented when you know that your input is a one hot vector. I think that people have just found that it's not useful to add the positional encoding beyond the first feed-forward layer. Like adding it in multiple positions, I think just doesn't seem to help based on that's my understanding. Yes. Is this used for both encoding and decoding? Great question. Yes. I don't think I have the full picture, but like this is typically added to both transformer encoders and decoders. Yeah. Shouldn't we be able to determine the position of a word in a sequence because self-attention, it'll have the highest similarity with itself? Yeah, interesting point. So there's a couple of things there. So the first is maybe you can sort of determine like, well, actually the first thing I guess is that the query and the key are produced by different functions. So there's kind of no guarantee that you'll be most similar with yourself, because the query could be looking for something that's specifically like not the key that was generated by the same input. The second thing is that you can't really determine the position of like any other words or any other tokens in your sequence. Like maybe you can figure out where you are, but you can't figure out anything else. And it's kind of useful, I think, in general to like know whether or not a particular token comes like right after this position or like, you know, way, way down in the sequence. And there's kind of no way, based on what we just described, to actually do that type of thing, right? So here, when we add the positional encoding, we're getting information about the positions of all the different tokens in the sequence, right? And then we're sort of like putting an ordering to it, which generally should be quite useful in terms of like figuring out what the right, you know, keys and values are, or what the right keys are for comparing to the different queries. Is self-attention done for every item in a sequence? Yes. So I think there's some kind of misunderstanding here that I haven't fully grasped. So like self-attention produces a different query at every time step based on the particular token at that time step, right? So let's say for a second that your query and your key functions are the same. They're not, right? But for simplicity, let's say that they are. So then you're going to be most similar with the key at your particular time step, right? The query and the key at any time step, they're going to match the best, right? Which is, by the way, not how it works, because then you wouldn't be able to actually like mix information across time steps. But even if you did that, right, I know that at time step 2, that K2 is most similar to what I'm looking for, right? But I don't actually even know where K2 came from. Did K2 come from the second position, or did it come from like the last position, or where actually was it produced from, right? And then also along those lines, I might know that I'm most similar with K2, but what if I'm also pretty similar with like K3? I don't know that that came from the third position or the last position or any other position, right? Because there's no like information about these positions that's actually put in anywhere for the self-attention process, right? So that kind of becomes the problem. And then add on top of that that the query and the key functions are actually different, then things become even more complicated. Cool, let's leave this behind and talk about another important detail, which is easier to grasp. So our self-attention looks like this, right? The way that we produce each one of these A's, right, from 1 to capital T, based on the input sequence, right, is a weighted combination of the different values that I have, where the weights come from the similarity between the query and then all the different keys, right? So when I'm producing A2, the second thing in that output sequence, when I'm producing A2, I'm comparing Q2 to all the different keys, producing these weights alpha through a softmax, and then doing a weighted sum to extract, the weighted combination of V's that I think is most relevant here. So there's an issue when we think about this approach and what it's doing, which is that oftentimes what's going to happen is these alphas, they're going to be quite spiky, where one of the alphas is very close to 1 and the other ones are close to 0. Okay, why? It's just because softmax tends to do those types of things, right? Because we're passing things through the exponentiation function, that kind of tends to blow things up a little bit. So in practice, what that means is that this type of attention module might be pretty good at picking out a particular V, okay, for what the A should be. But it's not going to actually be all that good at combining different pieces of information together. Like, oh, I need V1 and like V5, and I want to combine those together in some way in order to mix that information into the output that I want. Okay, it's not good at doing that. How would it approximately do that? It might say like alpha 1 is like 0.5 and alpha 5 is 0.5 or something close to that, and then just like average these values together. But averaging is also not necessarily a good way to combine V1 and V5, right? That might actually sort of lose the information of both. What I could imagine doing instead, which might give me both of those pieces of information, both of those values, is to concatenate them, right? So that I have both of them sort of uncorrupted by each other. But there's really no mechanism in here in the self-attention module that's actually letting me do that, right? All it's really letting me do is extract maybe like one value at most, kind of cleanly. Everything else is not really facilitated. How do I resolve this? I use this idea called multi-head attention, which basically just says, let's actually not use a single attention module. Let's stack a whole bunch of attention modules all on top of each other, okay? So it's basically just this thing. Okay, we have essentially different key query value functions for each one of these different, what we call heads of attention, of self-attention. Okay, each one of these can potentially be focusing on different types of information and extracting different values for this particular query at this particular time step. Okay, and then when we extract those different values, what we can do is we can then put them all together by concatenating all of them, and then all of a sudden we are able to extract more than just one time step of information. I'm not restricted to just looking at V1. Maybe one head can be looking at V1, the other head can be looking at V5, the other head can be looking at the last V, et cetera, and it allows me to combine information from different time steps much more effectively than if I was only using a single attention head. So all of these key query and value functions in all the different heads, which again are often just these linear layers that we have, right? They have their own learned parameters. They're all learned independently, but because they're sort of all working together, essentially what they learn is to work together in order to extract the most useful information as a whole. And the final thing that I actually output, so here in this picture it's A2, right, because this is a picture of the second time step, but in general every AT, right, is obtained by concatenating the outputs from every head and then potentially feeding this through another linear layer just as sort of like a information, processing kind of stage, although oftentimes that's not even needed. We can just concatenate the outputs from all of these heads together. An important detail about multi-head attention is that typically what we're going to do is we're going to scale down the D, okay, the dimensionality of the key, query, and values in proportion to how many heads we have, okay? So for example, if I had one head before and I was doing, 512 as my D, then maybe when I go up to 8 heads, like 8 different attention modules in parallel, I'll scale that down to D equals 64 in order to keep all the, computation budget roughly the same. But this is kind of the detail that allows me to, for every particular A that I'm outputting, right, actually potentially focus on a number of different positions in my X, right, in my input, and be able to combine those information in some intelligent way in order to produce the A that I'm actually looking for. That's kind of the big picture. There's some other details that we're not going to cover in a whole lot of detail. But they're all things that you sort of saw. I mean, Sean O told you a little bit about these things: layer normalization, dropout, skip connections. I also told you a little bit about skip connections when we talked about ResNets. These are all details that are quite important for getting maximal performance out of these transformers. And in code, it looks a little bit something like this. So this is like PyTorch code, which you will become familiar with if you're not yet familiar with it. By the way, Homework 5 had like a tutorial, right, or something like that. So hopefully you've seen things like this before. The important bit is kind of this like forward function of like one piece, one block in your transformer, which does layer norm, and then, whatever layer you're applying, either feed forward or self-attention, plus dropout, and then the skip connection is just like the input plus all of that, right? So this is what things end up looking like. This piece of code is from this URL that I put at the top called the annotated transformer. I think it's a great resource for learning about the transformer. It's got code alongside all these explanations that ends up being really, really useful. So if you're curious, I would encourage you to check that out. Okay, so that's a lot of the details about transformers. These details are relevant to both encoders and decoders, okay? So now let's talk a little bit about what decoding actually looks like from a transformer. Let me show you an example of what decoding can look like from a transformer. This is from actually I think it's from GPT-2, so we're sort of like one generation behind at this point, but I still think that it's quite impressive. One thing they can do if you have a transformer decoder is generate text conditioned on some input piece of text that you give it. So here the input that we condition the model on says, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. So this is the input that we're giving to our transformer decoder, and then we're basically asking it, from this point, now you generate the rest. Okay, generate the rest of this text in a way that you feel like will be plausible. There are kind of some interesting things about this. I mean, grammatically and, story-wise, it seems pretty good. But I do like some of these other bits, like, near the, like after a couple of sentences is generating things like University of La Paz. Why is it generating University of La Paz? Probably because in the input, it saw Andes Mountains, right? So it's learning kind of these long range dependencies, right? Like Andes Mountains came way earlier in the sequence, and it knows that later on it should say something like University of La Paz, because it can learn, because transformers are very effective at learning these long range dependencies, because they're processing the whole sequence as a whole layer using self-attention, right? So this is kind of the big bit behind what makes transformers effective. And in particular, transformers turn out to be really good at these types of decoding kind of generation tasks. So what does a transformer decoder actually look like? Something like this. So it's, a different color box. And what we wanted to do is basically like output a whole sequence. Here we're going to call it Y because it's almost like, the labels that we're outputting, it's like sequential. It's not really labels, but let's call it Y to sort of distinguish from the X's and the Z's that we had before, okay? We're asking this decoder to basically produce some amount of output for us, like Y1 through Y capital T. How does it actually do this? Well, the basic idea is that we're going to have this decoder produce Y's one step at a time, okay? It's going to produce Y1, then it's going to produce Y2, then Y3, and so on and so forth. Every time we call this transformer decoder, it's going to give us the next Y in the sequence. How does it know what the next Y is? It basically has to know everything that it's generated previously, okay? So what it's going to do is something along the lines of like generate Y1, and then Y1 gets fed back into itself in order to generate Y2. Y1 and Y2 then get fed back in to generate Y3, so on and so on and so forth. In this way, we can almost think of it as something like generating one word at a time, conditioned on all of the words that we had previously. So the decoder's generated output so far is fed back as input into the decoder. When we're trying to train this decoder, we're feeding in the ground truth. Okay, so we're feeding in part of a sentence and then asking it, what's the next word in the sentence? And then we're comparing what it generated to the actual ground truth next word in that sentence. And that's the way that these things get trained. Yes? Yeah, this is a great question. So in the transformer encoder, right, when I'm producing like a representation Z at some particular time step, that representation Z can depend on all the tokens in my input, both in like the past, so to speak, right, in a temporal sense, as well as the future, right? Here in the decoder, I actually have an additional complication, which is that I don't want anything that I generate to depend on the future, especially because I'm going to use this to generate text and I don't yet have the future, right? The future is what the decoder is going to generate. I don't know what that is, right? So the decoder actually architecturally is going to have to be different in order to make sure that anything that gets output can only depend on the things that came previously. And we're going to talk about how that gets done. So what does this actually end up looking like, transformers for decoding or generation? So like we said before, basically what's going on is whatever the transformer has already generated, which we'll call like Y0 through YT minus 1, Y0 is typically something like a special token like start in order to tell the decoder start generating, or maybe it's something along the lines of like everything that was fed in as the input prompt, right? In a shocking finding, whatever, right? And then we give it all of that up to what it's generated so far and ask it to generate YT. What does this process actually look like? Basically kind of looks like what we had before, where we have these, interleaved feed forward and self-attention layers that are processing this input that we give it, this input sequence Y0 through YT minus 1, in order to get what? We get Y1 through YT, okay? So remember with a transformer, we're always getting the same sequence length in as the same sequence length out as we fed in, okay? So this is a little bit weird because we have Y1 over here. We also have Y1 in the input. These things don't necessarily have to be the same, right? Like maybe the y1 as part of the input is the ground truth, and the y1 over here is what we're predicting, and maybe the model's not that good, so it's not predicting the right thing. Basically, what we're going to do is we're going to ignore every single part of the output that the decoder produces, except for that very last thing, the yt over there. And the yt is the only thing that we're going to take in order to put it back onto the input sequence in order to have the model generate yt plus 1, and so on and so forth. So in the end, this might look a little bit something like, this whole, output sequence that we're looking for. Basically, if the model gets y1 through yt minus 1 wrong, we don't actually even care. We're only looking for that yt, which might be something like pos, if yt minus 1 was la. And then this yt gets added to the input in order to do generation for the next time step. So here what we're describing is how the model will be used at test time. Okay? At test time, we're asking the model to generate text. We don't actually have this problem of the model looking into the future, because here the future doesn't even exist. Right? Like I don't have yt plus 1, because yt plus 1 is something that the model is going to generate later. So I don't actually have this issue of, well, I need to prevent my model from looking at the future. The future isn't even there. However, this is a problem during training, because during training, I'm feeding in whole ground truth sequences to this model. So the future does exist, right? So what I need to do is figure out how I'm going to prevent the model during training specifically from looking at the future. And that's where this detail about masked attention comes in. This is kind of the architectural difference between encoders and decoders that makes it such that the decoder can't look into the future, but the encoder can. Okay, this is the important bit. So during training, entire sequences are passed into the model, and the model must be prevented from, quote, looking into the future when learning how to generate. Okay? Imagine if on this previous, or imagine if I feed in like a whole sequence like y0 through yt minus 1 as input, and then I ask the decoder to generate y1 through yt. So it's basically learning how to predict all these next words, right? If I didn't do anything special, it could just learn something like, well, copy y1 from the y1 in the input, and copy y2 from y2 in the input, and so on and so forth. It's just learned something really, really dumb, right? This is obviously not helping it learn how to generate things, so I need it to be able to only to look at y0 when generating y1, and y0, y1 when generating y2, and everything up to yt minus 1 when generating yt in general, right? So this is what I need to be able to enforce. And one way to do this is to basically what we call mask keys and values that correspond to future time steps. So what does this end up looking like? Here's our self-attention. Here's what it looks like. The basic idea behind masked self-attention, or at least I think the easiest way to think about it mathematically, is that every time step that corresponds to a future time step, so here my time step is 2, right? Any time step that's 2 or larger, we're going to replace this score, this dot product that I get, with negative infinity. Okay, I'm just going to pretend that that score is negative infinity. Okay, what does that mean? It means that the corresponding weight is by definition 0, because I'm passing that through an exponentiation through a softmax, right? So in this way, all of the weights that correspond to future time steps will be 0, and so then my A that I output is definitely not going to depend on any of those future values, right? So in this way, I can prevent my model from looking into the future when trying to predict what should be the next word in this particular sequence. And so that's what we do at training time. This masked attention is very important for decoder training in order to make sure that it doesn't just learn the stupid thing of copying things over. All right, we'll do one more slide, and then I'll let you go. The original transformer is something that we call a sequence-to-sequence model. Okay, so the original transformer was designed for translation, translate English into French, or different things like this, translate one language to another. The idea behind a sequence-to-sequence model is that I take in a sequence as input, here, for example, like an English sentence, and my model needs to produce a sequence as the output, like the corresponding sentence in French. That's all sequence to sequence means. It's just sequence in, sequence out. Typically, how we solve these types of sequence-to-sequence problems like translation is using an encoder-decoder architecture, and basically, you already know what that means because we've learned both about encoders and decoders now. And so this is what the original transformer was. It was both an encoder and a decoder for translating sentences from one language to another language. And so basically it looks something like this. You have an encoder that takes in the input sentence and then produces the representation that hopefully will be useful for the decoder to then translate into the other language, the sentence in the other language. And I'll tell you next time how this actually works in detail. Okay, that's all for today. Thanks.